This problem is in your notes packet. We're going to go over the ideal gas law, how to use it with Dalton's law. So anytime I say a gas is collected through water displacement, or if it's collected over water, something needs to go off in your head that you're going to have to use Dalton's law, which is total pressure equals pressure of all the gases. And if it's over water, it's going to be the pressure of your gas plus the pressure of water. And so let's look at this problem. Okay, gas is collected through water displacement. How many moles of gas, so I'm looking for N, are collected at a temp of 295 K, volume of 1.3 liters, and a total pressure of 1.4 atm. So P total is 1.4. At 295 K, the water pressure is 19.8 mmHg. So let's label pressure of water 19.8 mmHg. Now you would list your variables, and I hope you need to, when you see there's total pressure and pressure of water, remember to use Dalton's law, which is total pressure equals pressure of the gas plus pressure of the water. Well, it's pressure of all the gases, but in the case of collecting something through water, you're going to have a gas and you're going to have water. And so we want the pressure of the gas because that was what was collected. We don't want the pressure of the water in there. And so what we're going to have to do is, to get the pressure of my gas, which is what I want to use, I'm going to have to take the total pressure and subtract the pressure of the water from it. Now, pressure of my gas is what I'm looking for. The total pressure is 1.4 atm. Pressure of water is in mmHg, so you're going to have to we have to change that to atm. To go from mmHg to atm, you have to divide it by 760. And so 19.8 divided by 760 is 0.026 atm. So to get the pressure of my gas, I'm going to take my total pressure and subtract the pressure of water, 0.026. And what does that equal? Pressure of my gas is 1.374 atm. Okay. Now, let's look back what we have. We have the pressure we want to use, 1.374 atm. We have volume. We have T. We want to find N. PVTN, this is ideal gas law. PV equals nRT. We're looking for N. We have pressure. We have volume. We know R. And we know T. So we can now plug in these variables to solve for N. And so I'm going to do that on a separate sheet of paper. Ideal gas law, PV equals nRT. I'm using the pressure of my gas, not the total pressure, not the pressure of the water, the pressure of the gas, which is the difference between the two. 1.374 times volume, which was 1.3 liters, equals N, what I'm looking for, R, which is a constant, times T. And then from there, just plug in and solve for R. And that would give us N equals, I think I typed that in wrong, hold on. I didn't. 0.70737 moles with significant figures 0.074 moles of gas. And then from there you could always go change it to grams if I told you what gas it was or whatever. Okay. I'm going to go over with you, and I want to do this on video and not just through PowerPoint, the ideal gas law with stoichiometry. Yes, you're going to have to use stoichiometry. Sorry, get over it. I told you it was never going away. You will only have to use stoichiometry with the ideal gas law. You're not going to have to use it with Dalton or with Boyles or Charles or anything like that. And so something important to remember about the ideal gas law, PV equals nRT. This is a gas law. And so when I am using volume, that has to be volume of a gas. Moles has to be moles of a gas. You will realize that you're going to have to use some stoichiometry because I'm going to give you like moles of a solid. You can't use moles of a solid in the ideal gas law equation. And so if you see something, I give you like grams of something and it's not, or moles, or I don't know, whatever, and it's not a gas, you're going to have to use stoichiometry because you can't use it in this equation. And honestly, it is just easiest if we do examples, an example for you to see. And we're going to do two together. These can kind of be long, so that's why I gave you a lot of space between them. Okay, this first one. Methane will go through combustion and produce CO2 and water vapor. How many liters of carbon dioxide would be produced when 25.6 grams of methane combusts at a temperature of 24 Celsius and a pressure of 1.5 atm? So I'm looking for volume, my liters of CO2. I'm going to go ahead and label that volume of CO2. That is missing. That's what we want to find. And you should know carbon dioxide is a gas. We have 25.6 grams of methane. Let's just write that down. My temperature is 24 degrees Celsius. My pressure is 1.5 atm. So V, T, P, there's no 2's of anything. This is going to be an ideal gas problem. You should think that immediately. So we know R 0.0821. And we're going to need N. Now, I'm looking for the volume of CO2. If I want to find the volume of CO2, my N has to be moles of CO2. It can't be moles of methane because I'm trying to find the volume of CO2. So it has to be moles of CO2. I don't know how many moles of CO2 are in this problem because I didn't give you that information. But I did give us grams of methane. And so list your variables, and then looking at this, we're kind of stuck right now because we don't know V and we don't know N. And so what you should do is, well, let's go back to the problem and let's write an equation out because I gave you the info to write a balanced equation. So methane is going through combustion. Methane is CH4. You should know a combustion reaction is plus O2. And then in case you forgot, I told you make CO2 and water. And then balance the equation. 4 hydrogens on the left. So I'm going to put a 2 here, and then oxygen needs to be balanced, a 2 here. And so I've got my equation now. Now let's come back and look. I told us we had 25.6 grams of this. And we need to find the volume of CO2, and we need to find my moles of CO2. Now you can't use stoichiometry to solve for volume. The conversion 1 mole equals 22.4 liters is only true at STP, which is 0 Celsius and 1 atm. The temperature is 24 and the pressure is 1.5. So this is not at STP. This conversion is not true. Honestly, you can forget about that conversion because I'm going to tell you right now, none of the problems I'm giving you are at STP. So I cannot go from grams of this to volume of this because that's not true. This is only true when you're at STP. But I can use stoichiometry to go from grams of methane to moles of CO2. And then once I have my moles of CO2, I can find my volume of CO2 using the ideal gas law. And that's what we're going to do. So multi-step problems. So we're going to find my moles of CO2 using my grams of CH4 through stoichiometry. 25.6 grams CH4 times grams of CH4 in 1 mole CH4. I'll plug that number in a second. And then I'm trying to go to CO2, so 1 mole of CH4, there's not a coefficient in front of it, is 1 mole of CO2. And we got to stop there. Now let's go find the molar mass of CH4. Carbon, if you don't know that by now, it's 12.011. I don't know what you've been doing. Plus 4 hydrogens. The mass of this is 16.043. And that is 1.59 moles of CO2. Now I have moles of CO2. And so I've got N, thinking about my ideal gas law, PV equals N R T. I know pressure. I'm looking for volume. I now have moles. I know R. I know T. We can now plug into the ideal gas law and solve for volume. But let's check everything. Temperature needs to be in Kelvin, because right now it's in Celsius. That is 297 K. So pressure 1.5, volume we're looking for equals moles 1.59 times R 0.0821 times T 297. I plug that into the calculator and I get my volume is 25.8 liters of carbon dioxide was made. Now this is as hard as ideal gas law problems can be. And so there's a few hints. When am I going to have to use stoichiometry? I kind of knew I was going to have to use stoichiometry because I was missing volume and I was missing moles. If you're missing more than one letter in the ideal gas law, you're going to have to use stoichiometry first. And then second, make sure you always label. So like volume is CO2, moles has to be CO2. They have to be about the same substance. Same with pressure and temperature. You can't use like volume of oxygen, moles of CO2, pressure of water. That wouldn't work. Everything has to be about the same substance. So pay close attention. If I say liters of CO2, you might want to write V CO2 to kind of clue yourself in that something's not right. But there's going to be two types of ideal stoichiometry problems. Problems just like this one, where you have to do stoichiometry first. And then we're going to go through another example where you're going to have to use stoichiometry second. So you could see it either way. Just get ready. And I'm going to pull that problem up. It's on the next page in your packet. Okay, so when calcium carbonate decomposes, carbon dioxide is formed. How many moles of calcium carbonate will be needed to form 3.12 liters of CO2 if the reaction occurs at a pressure of 742 mmHg, temperature of 300 K? So we're looking for moles of CaCO3. I have volume of CO2. This is where labeling is helpful. 3.12 liters. The pressure, 742 mmHg. Temperature, 300 Kelvin. Vp and T, you should look at that and say this is going to be an ideal gas law problem. R is 0.0821. And then let's go ahead, we're going to have to change our pressure to ATM because it has to be an ATM for the ideal gas law. So divide that by 760, pressure is 0.976 ATM. Okay, So, looking at this, I've got pressure, I've got temperature, I've got R, I've got V. I have V of CO2. I don't want N of CO2, I want N of CaCO3. But we don't know the volume of calcium carbonate. Let's go ahead and just write this balanced equation out. You still need to know how your polyatomics decompose. But I kind of clued you in because calcium carbonate, which is CaCO3, I told you it formed CO2. The other product is, in case you forgot, carbonates decompose into CO2 and a metal oxide. So calcium oxide, which is CaO. And this equation is actually balanced. Okay. And I know I'm going to use my ideal gas law. So, a few things. One, I'll make sure on the test it's very clear. Calcium carbonate is not a gas, it is a solid. But that doesn't tell you that in the problem, and I wouldn't expect you to know that until the second. But I'll make sure on the test that's clear. Also, we have V, we have P, we have R, we have T. We're looking for N. If V is CO2, and I have everything except for my N of CO2, I actually can use the ideal gas law right now because I have pressure, I have volume, I'm going to find N, which is moles of CO2, and then I know R, I know T. And so let's do that first. 0.976 times my volume, 3.12, equals N, and I'm going to run out of room, 0.0821, times my temperature, which is 300. .976 times 3.12 is hold on, 3.04512 equals N times 24.63. Divide each side by that. N equals 0.124 moles. And then stop and think. You found volume of carbon dioxide. So this has to be moles of carbon dioxide. It can't be moles of calcium carbonate because this is volume of CO2. So that's my moles of CO2. But if you know how many moles of CO2 there are, you can use stoichiometry and find moles of calcium carbonate. And so let's set that up really fast. I've got 0.124 moles of CO2. This is a balanced equation, so 1 mole of CO2 equals 1 mole of CaCO3. And it ends up being the same number because it's a 1-to-1 ratio. But that's not always the case, and so you shouldn't expect that. And that is how you would solve this problem. Now, some hints with the ideal gas law and stoichiometry. If you're missing more than one letter from this, so let's say you're missing P and N. If you're missing 2 variables or more, you're going to use stoichiometry first. If you're missing 1 variable, you're going to do the ideal gas law first, and then stoichiometry. And then just be really careful and label your substances, because if it's volume of oxygen, your moles will be oxygen. You can't have volume of O2 and sulfur moles of CO2 at the same time. And it really helps. List your variables, label stuff, and I promise you can figure this out. And I do want you to try some on your own.